Alrighty, first lab, and we're all here with our bonus student. Okay, what we're going to be doing is looking at motion. And it's a very simple thing. It's where we start in physics. And there's a couple words that I have to now carefully define because we haven't had them in class yet that we're going to be using. So the first is distance. Okay, y'all know what distance is, right? Distance is how far something travels. So that's a pretty simple idea. Displacement is a vector form. Do you remember from yesterday's class what vector means?
That I remember reading it's like how much the force or something.
No.
So it's arrow.
It has to do with arrows because vector means it has a direction. And so one of the stupidest demonstrations I ever do is I say, okay, I start here, and let's say that I'm running around the track. And so I go around the track, and if we're Prairie Life Fitness, doing one lap around the track means that I covered a distance of 1/13 of a mile because it's a really short track. This was even shorter. So my distance I covered, in theory here, is at 1/13 of a mile. My displacement is the vector that points from where I started to where I ended. And its length, its magnitude, magnitude is the word that means how big the number is. Its magnitude is the length from where I started to where I ended. So really simple, dumb question. What's the distance from the starting point to the ending point in a straight line? If I did one complete lap. Okay, I ended where I started, so the distance between the starting and ending points is 0. So the displacement for that lap is 0, while the distance was 1/13 of a mile. Or as the real case would be here, about 5 meters. So that's the difference between displacement and distance. Now, displacement also has direction. So if I start here and I just move, okay, that's about, let's say 5 meters. I moved 5 meters. What's the distance I traveled? Obviously, 5 meters. What's the displacement? It's going to be 5 meters in that direction. So the magnitude is 5 meters, but we also have to add the direction with the displacement. So I think the experiment itself simply talks about position. The position is where you are with respect to where your reference position is at any time. So what you're going to be doing in your experiments, for instance, is you'll be starting, and this thing is going to measure your position with respect to it. So if it's right on my hip, the position would be 0. It actually won't read things that close. And so here, my position is about 1 meter. I come back here, it's about 2 meters, about 3 meters. So that's what's measuring with position. Now the next word here, speed, velocity. This side here of what I wrote, we call scalars. I'm going to really zoom in so I can write somewhat legibly. And then zoom back out. Better, right? A scalar means it does not have direction. In contrast to this side here, which are vectors, which means they do have direction. So the difference in a scalar and a vector is having direction. And so displacement was a vector, whereas distance was a scalar. Velocity is a vector, whereas speed is a scalar. Now speed, we all have a good feel for speed. I get in my car. Initially, my speed is 0. I press on the gas pedal. My speed changes, gets faster and faster. But we haven't really defined exactly what speed is. We have a feel for it. We know what it is. But in physics, we have an equation for it. In physics, we have lots of equations. And to a physicist, i.e. to me, those equations have symbols that mean lots. The symbols to me are very meaningful. And I understand that to you, they're not very meaningful. So here's the symbol for speed. V. At first glance, it doesn't make sense, except for remember, speed and velocity are the same thing except for the velocity has direction. So, and I will learn your names by the end of today. Right now, I just know Danny and Samuel, basically. I'll learn everyone. The difference is the arrow on top, which means that it has direction. And so velocity, V with an arrow over it, means a vector. Speed just doesn't have the direction, so we use the same symbol but take the arrow off to say it's just how fast it's going. So it actually makes sense to use V for speed, but then it brings up imprecision in how I talk. Because I write down V, my brain says velocity. And so I find myself saying velocity when I mean speed. And because I start mushing those together, I'll sometimes say speed when I mean velocity. But the two mean something different because velocity has a direction tied to it, speed does not. What is the definition of speed? That. And once again, to me, that makes perfect sense. But I am guessing to you it doesn't make perfect sense. So that triangle, does anybody know a name for the triangle? Change. Okay? The meaning is change. It means the change in. It's the capital Greek letter delta. I always have to share, I think it was my first year here at Union, I was talking about something and I used this symbol here, which is the Greek letter omega. And I had a student come up to me after class. She didn't want to embarrass me, but she said, you know, I used to be in a sorority and they made us memorize the Greek alphabet, and that's not omega. And, you know, at this time I had already been teaching for 8 years somewhere else, so I wasn't really nervous like my first day as a teacher. I said, yes, that's the lowercase omega. And she was like, there's lowercase in Greek? Right, because she knew the uppercase for omega, but didn't know that there was lowercase. That's a capital delta. The lowercase delta is something like this. But that's just I think it's funny. I'm mocking. That delta means, as Samuel said, change. It's always the final minus the initial. So we'll sometimes write this as XF minus XI over TF minus TI. Because change in, delta, is always the final state minus the initial state. Never the initial minus the final, always the final minus the initial. But then we have only the deltas I've explained. That's 2 out of 4 symbols. The others, at least one of them you'll get for sure. What do you suppose X stands for? Go ahead, Leslie.
Displacement.
Okay. X, if I have a vector over, an arrow over, it's displacement. If I don't have an arrow over it, then it's distance. So the X is the distance or the position. So change in position or change in distance divided by, and the T should be the obvious one. T is what you think it is. Time. Yeah, thankfully no one said temperature because that would have also made sense, but it's not it. So time. So speed, if you write this out in words, you get speed equals change in position divided by I'm writing it all in one line. So that's what that equation means if you write it all out in words. And of course, when I'm teaching, I usually say the words. And then I'll write it down with only a total of 5 things. You know, V equals delta X over delta T. And in my brain, I said and wrote exactly the same things. And it's something that over time, hopefully, you will get to feeling comfortable with. But I understand that right now it's not comfortable. So it's something to learn. Speed is change in position divided by change in time, which makes things pretty simple to calculate. Like if I am traveling at a speed of 60 miles per hour, right? MPA is miles per hour. Probably familiar with that. And if I drive for 1 hour, then the total distance I'm going to travel, if I take that equation, the distance change in position divided by the change in time is my speed. So if I take the change in time and multiply it across, I'll actually show this. And of course, I'm going back to doing equations. We use the equations because it takes a lot less writing. If I solve this for change in time, or excuse me, change in position, to get delta x by itself, what's the mathematical step? Multiply by? Yes. So what I do to one side of the equation, I have to do the other. And then the delta t's cancel on this side. And I have the change in position is equal to speed multiplied by change in time. So if I'm traveling at 60 miles per hour for 1 hour, then I cover a distance of 60 miles per hour times 1 hour equals 60 miles. So speed is, we call it a rate. It's the rate at which you are covering ground. Acceleration, you're specifically told in this lab not to use the word acceleration. So you know what I'm not going to do? I'm not going to define acceleration today, simply so you don't, think about that to confuse you, just focusing on speed and motion. Now, what are you going to do in lab? What you're going to do is make graphs of your motion using this equipment. You're going to have a Sonic Ranger is what it says there, hence the title of today's lab, Sonic Ranger. Nothing to do with silver. This here is our motion sensor. On the top, it has a little switch. The switch has either the picture of a little cart or the picture of a person. You're going to be the object. So guess which way you want the switch to be? On the person. So I switch it over to the person. I'm just going to set it up here for now. This just plugs in. It can go to any one of these. It doesn't really matter. Only 3 of them are set up because I thought there were only going to be 7 people here. With 8, we'll just use another one. Use this one. One thing I actually recommend, Alex set these up, the front tables. I recommend just using the tables on one side. That way you can walk all the way across the classroom without having people working opposite you. So I would just say after I get done, we'll move that stuff to behind you ladies and then move this stuff to the back or one of the further back tables. And that way everybody's just going the same direction and nobody's going to interfere. Okay, so that's my Sonic Ranger as it calls it. The computer controls it. It's going to send out a little chirp, a little sound that's inaudible to us. And that sound wave is going to come out, hit you, and bounce back. And it measures the time for the sound to travel out and back. The sound is traveling at a constant rate, constant speed. So it's going to take the time that it took to go out and back, multiply the speed by the time to get the distance. It does divide by 2 because the sound had to come out to you and go back. And it calculates how far away you are. And so it's going to make a graph that shows you your position every 1/20th of a second. It's going to measure your position every 20th of a second. And then you're going to walk back and forth and see what the graphs look like and describe them. Now, the instructions here generate real-time graphs of each motion depicted on the following pages and write a description of each. So, and notice it says use these terms. So I highlight the terms you're supposed to use in your descriptions. Now, you shouldn't just have rest. You should have a little more description than that. So here's an example of the first graph. It has a graph. The position, it starts at a distance of 1.5 meters away. It ends at a distance of 0.5 meters away. So if you describe that motion starting at 1.5 meters away and getting to 0.5 meters away, is it moving toward or away from the sensor? Toward. So you would say move toward the sensor. Now the second part is at constant speed. How would you determine that? Some of you may know, I don't want the person who knows to raise their hand say, and everybody else say, how does the person know that? Because we haven't talked about it. So I'm just going to tell you. Go ahead, Leslie.
Do you want us to write that yellow cartoon? We'll make sure each person in the group moves to describe that too.
Well, each person in the group is going to have their own report, and we want each person to actually move to match it. So we'd want Leslie to do it. Huh?
You want us to write that down in here too? Or
No. Only the thing in the red box is what you wrote down.
Okay, awesome.
Okay, yeah, that was your question.
Yeah.
Yeah, Alex, we need a fourth station. You got that. Alex is our TA. He is your friend. He'll be doing the grading. If you don't like the grading, you'll be having beef with Alex. But you should like his grading.
Email him, by the way. His grievance is not me.
Don't know why he says that. Okay, but I do want you to have each person. So in your group, you'll have two people. So let us say that Sammy. Do you go with Sammy, Samuel, Sam?
Sam.
Okay. So Sam and Danny, let's say that they're partners. So Sam will do it and see if he can match it. And then he'll say, yeah, I got it. And then Danny will do it and see if she can match it. And of course, as soon as, actually, Alex, set them up all on this side of the classroom.
Oh, yeah, that would be a fucking picture.
Yeah. So, it's just we want both people to have the full-on experience. The lab itself doesn't take much time, so we're not asking a huge amount to have both people do the motions. Now, since you're going to be simulating this, you'll be able to figure out what it is, but I'm still going to explain how it works. We have a graph here that shows the position versus time. Have you guys worked with graphs in a class before? Okay, when you worked with graphs in a class, one of the things you found was the slope. What's the equation for the slope? Rise over run. So I can take this line and I can say, okay, this here is my run and this is my rise. Now, if I look at what I have on the axes of the graph, the run here is measuring a change in time. And so the run is equal to the change in time. The rise is measuring a change in position. So the rise is change in position. So using the substitutions, the slope is change in position divided by change in time. But what did we see before that was change in position over change in time? That was the speed. So the slope of the graph is the speed. So if you look at this graph, what's the slope doing? Okay, the slope is measuring the speed. That is a true statement. But in this specific graph, how is the slope behaving? Okay, it's a decreasing slope, which means that it's a negative speed. And is it changing? No, it's constant because the slope is how steep it is. So how steep it is staying the same, right? It's not going like this. It's constantly staying like that. Now, you're going to do all these, but I'm going to quickly just look at them. What's the slope doing here? Okay, it's staying the same at what value? 0. So if the slope is 0, what does that mean? There is no speed. The speed is 0. And so this would be, what do you call when the speed's 0? Still, the word it said to use is rest. So you just say it's at rest the entire time. Really quick and easy, right? What's this one doing? Okay, the object is moving away because it now has a positive slope. And is the slope changing or staying the same? Staying the same, right? So the goal for today's lab, part of it is to get these things so you can actually do it and see, yeah, that's actually what it's doing. What's the difference between the graph here in number 2 and the graph here in number 3? Yeah, it's a steeper slope here for number 3. Number 4, what's that doing? It's changing slope now. So that means the speed is changing. And so you're going to need to describe that and also do it just to make sure that your description is what you think it is. Now the second 3, there's 3 graphs here, I believe. Yeah. The second set, part B, which has 3, now it gives you a description and you need to make the graphs. So what you're going to do is you are going to make the graph physically, and then you'll copy here what it looks like. So you'll have and then you'll put what the shape looked like that you made. So I'm going to do something that's not at all what this is doing. Okay, that's not a function for people who are mathematically inclined because you can't have it at 2 positions at the same time, right? So that's clearly not real. But you're going to draw what the graph actually looked like. I don't care for you to put the numbers on the axes. Just have something like this. But I'm also going to have you save the graphs from your computer and upload those graphs on Moodle. When you're done, you're going to turn in the papers, and before you leave, also upload your pictures to Moodle, and then we'll combine them and grade them. So make sure that you do save the graphs, and I'll show you how in just one moment. So you have 3 cases there. Then you sum up, you describe what's the difference between forward motion and backward motion looking at a graph. So what you're going to say is I look at the motion of the graph of forward motion, I look at the graph of backward motion. What's the fundamental difference? Then what's the fundamental difference between a graph going slow and going fast? And then finally, you have this graph, and I label these A, B, C, D, E. It has marks on here, and you're going to say, okay, at this point, the motion was at rest. At this point, it was moving forward at constant speed. At this point, it was moving backward at constant speed. Notice that there's only 4 dots, and there's 5 options, so you're not going to use all of the options. And note also that speeding up and slowing down, it doesn't matter if it's going forward and speeding up or going backward speeding up. Speeding up means that it's getting faster. So that's not talking about direction, like going forward and slowing down is slowing down. Going backward and slowing down is still slowing down. And notice the last part we're not doing, so that's why I blacked it out. Now let's get to how you're going to do this, and then I will leave it to you. So here's what, oh, come on, hide. Here's what the software looks like that we're going to use. The software we're using is called Capstone. It's by Pasco. Sometimes when you start it up, there are problems. We don't know why. Alex can help you get past that if you run into a problem. Don't start it like 5 times. Start it, and if within 2 minutes, these aren't fast computers, if within 2 minutes it doesn't come up, call Alex over, and he will take care of things. So when you get the program opened up, the program you'll find on the desktop of the computer, there's a folder that says SCNC 111. You go into that folder, and then there's activity 3. Actually, it doesn't say activity 3 anymore. It says lab 01, activity 03, Sonic Ranger. So you open that baby up, and it's ready to go right now. Down here at the bottom, this red button is what starts taking data. So now it's taking data. Of course, there's nothing in front of it, so it's just seeing whatever it sees. Now I come here, I'm in front of it, and you see I'm a lot closer than whatever it's seeing. And I can move backward and forward, and it's just recording graphs to show my motion. So that's what you'll be doing you have two people in your group because one person will start and stop it while the other one's walking around, so you don't have these kind of gaps. So I hit stop. There's my data. When you're taking the data, one of the first things you want to do is make sure that you scale it so it fills the screen. So how do you make it fill the screen? Well, you can manually, by clicking on the axis here, you can stretch the axis. So I can stretch. If I get the hand, it'll actually just move it. So I'm cutting out stuff I don't want. Stretch. And there I have filling the screen my actual walking around. And I got rid of the extra stuff. I just don't have it there. Well, remember I said for the last three, you need to record your graphs and then upload those to Moodle. So how do you record them? Well, you go like this. See up in the top of the screen? Yeah. The top of the screen, there is a thing that's supposed to look like a camera. It's a black thing with a circle in the center. It's supposed to look like a camera. If you click on the little arrow there, it shows you three different options. A snapshot of the entire workbook page, a snapshot of the workbook page content, or a snapshot of the workbook page display. Either one of the bottom two would just be fine. I'm going to go ahead and take the display. The display will be just the single graph. If I had two graphs, only the one, see it's got that dots around it, only that one is the one to take a picture of. So now I'm just going to click on that camera icon. And you see that's the picture I took. But now it disappeared. Well, I want to know where it went because I have to somehow save it. This little thing beside it is your journal that shows you the pictures you've taken. So here's the picture, and I'll click here to annotate maybe, and I will put Richard, okay, that's Richard part B number, what, I think 7 is one of the ones in part B. So it's got my label there. Don't hit return. That puts the carriage return in. So now I go back to, I'm just going to hit the X up here to close the journal. You can delete runs here, delete the last run, or I can just make a new run. I'll just make a new run. So here's a new run that's just going to be made on the same screen. Now, I make this new run on the same screen. You're like, well, that's crazy. Now you have two sets of data on top of each other, and it's going to be all messed up looking, right? Right?
Yes.
Well, we can do a number of things. One thing I could do is say, okay, I've already saved, got my printout of run 1. I can delete it if I want. May want to, may not want to. Another thing I can do is come up here and see that was the little triangle with the rainbow colors. Kind of looks like Google Drive's logo. And I'll just take the check mark off of run 1. I just took run 1 off of my graph. Or I could go the other way, turn off run 2. I could turn them both off, but then I'd be really frustrated. So you can have them in there and not see all of them. We made a mistake first semester. I told, don't delete anything. There's only so much memory in these computers. We started crashing the program. So you do need to delete things at times. I can also come down here. I could delete the last run, delete run 1, or delete all the runs. So you have lots of control on what your data there is. Here is data with absolutely nothing useful. There is an autofit feature. If I have data that makes sense and it's no extraneous stuff, I can just hit this button here, and it made it so it filled the graph. Now, you see it filled the graph. The highest data point is there at the top. The lowest data points are here at the bottom, and it filled it side to side. So that's a good way to start for scaling. I'll take a picture of this. You see it shows me, yeah, it took a picture. I can look at my journal. Now I have the 2 pictures. And when we get all done, I said that you need to save yours and upload them to Moodle. So each of you is going to have a different set that you save. So now I need to save them to PDF. I don't want to export to HTML. Yeah, I want the printer one. And the printer one, just do the PDF PDFill PDF. Actually, the other printers they won't disappear on yours. The PDF, whatever, there should be something there to send it as a PDF. So you do that, and then just choose the pages you want. So if mine was only page 2 was mine, I just choose page 2. You'll have 3, your partner will have 3, so you just choose the 3 pages that are yours. Print, and then it comes up with a little dialogue, to name the file. This guy's my witness. It should come up with a dialogue to name the file. It's always frustrating when it doesn't do what it's supposed to do. Well, I trust it will. And that is the end of my presentation. So any questions? Yeah.
So we're going to be working in partners. Each of the partner has to have their different one.
Yeah, each partner will make their own.
Okay.
And you're working in groups of 2. I don't know why it never came up with a dialogue for me to name the file, because it should have. Something very kooky going on. Okay, so your groups are up to you. So just choose who you want to be in your group with you and get started.